welcome Diogo Braga.
So, thank you very much for this invitation to be here. I'm Diogo, a data and machine learning engineer at Epcont. My expertise at the company mainly goes through graph technology. And today I bring you connecting the dots, graph analytics for economic sustainability. And the agenda, I need the, that's important. And the agenda for today, so I will roughly explain to you what a graph is for some of you that might not know. Then I will go through some use cases and also show the advantages that graph can bring to your use cases. Okay, one. So why is graph technology relevant? So a graph contains detailed information about the business field, about the subject, and connections that describe the relationships between these data points. So because they are so flexible, graphs are being used in a broad range of industries and sectors such as finance, manufacturing, public safety, retail, and many others. So here, first, we can see an entity linking knowledge graph, which is being very used also because it comes from the previous RDF graphs. But this here is a property graph that joins very multiple different data sources into just one model. So for example, we have customer information, we have industry information, company information, functional, environment. And the graph gives us this feature of being able to interconnect all of our data in a very explicit way because, for example, if you would like to draw the business model of your company, you will probably have all of these connections. So the thing that a graph gives you is exactly this capability to be much more explicit and then, of course, take advantage of it. For today, I bring you two case studies. The first one related with supply chain, the second one related with fraud detection. Okay, so graph database. So what is a graph shape problem? How can we identify if a problem is suitable for a graph database? So graphs are used to model relationships between data, enabling querying and data analysis based on these relationships. So because these relationships are first-class citizens, they are identified with unique keys, which is different from conventional databases where we have to use foreign keys to then make this connection of the different data sources, different tables. So this is exactly the point where by making relationships first-class citizens, what we get is that graph databases can much more efficiently store, retrieve, and mainly traverse the data. So go through different data sources, through different tables, because this concept of table is then actually transposed to a graph. So for example, here in this small example, we have three entities which are called nodes or vertices. And then we have relationships between them, and also in these relationships we have properties. So all of these are actually first-class citizens and can be queried, can be addressed. And because this information is already in the model and we don't have, and is already explicit, we can much faster traverse it and then take advantage of it. And then you might ask yourself, okay then, what are really the use cases that graph databases are best suited for? So these graph databases are definitely best suited for problems where you have highly interconnected data that require real-time processing and high scalability. So, because most of the times, these problems, you can solve them with conventional databases, but the problem is that, and plenty of companies come to this problem, is that sometimes you have to wait days or even like weeks to get an answer for a query that has to run in millions of data. And in this case, because if the connections of data that you are interested are already explicit, it's actually much faster. So again, here a comparison of these three types that I was approaching. So only graph databases can handle highly interconnected data at scale and at a high performance. Conventional databases cannot easily model or store relationships without complexity, exactly because of what I was saying. Because if you have, all of your data in different tables, whenever you want to join them, then you have to go through these complex joins. And it's exactly the second point, that adding new relationships then requires even more schema and modeling effort, which in a graph database, if you have your data and you want to add something, you then add a new vertex, and you actually create a new relationship without changing any of your model. And of course, then performance comes into also question, because it gets much more efficient when you're dealing with graph databases. So we have our data. What can we actually do with it? This is where the analytics part, the algorithms part, comes into the equation. So graph analytics is a set of algorithms that we apply in a graph database that allows the exploration of relationships between our entities of interest that we identify. So being as organization, people, resources, and many more. So for example, here we have some of the capabilities that we can fit into a graph. So for example, whenever you have a problem, when you have plenty of dependencies, so we have an order of operation or we have a chain, then a graph database is actually a suitable case. It's something that it's much more adaptable than having tables. Clustering. If we want to cluster, if we want to find entities that are closely related to each other because of the features that they might share between them, we actually start clustering them too. Similarity. If we want to find similarity paths or patterns, again, if we also have highlight variant of dependencies. If we have distribution problems, if we have problems of efficiencies, then we want to match this flow. We want to track this flow. Graph algorithms also have high capability there. If we want to find entities that are the most relevant, centrality search, that's one of the capabilities. And for some of them, on the use cases, I will exactly show you this applicability. And when we come to this part, then it's exactly all of these algorithms use the connectivity, the relationships between all of these vertices, and that's why we are able to run queries much faster than actually being needing to do complex joins between tables. So the first use case is supply chain management. So what is the challenge here? In a supply chain management, if we think about a product, suppliers, products, components that all together bring up to this same product, all of these dependencies come up with, in the end, bring up deep hierarchical integrations and deep hierarchical dependencies into one last goal. But it's exactly about this, having different companies giving us even the same product, but like, how are they giving us this product? So our goal here is being able to gather real-time insights across all of these dependencies between suppliers, resources, locations, orders, maintenance, and even more, so that we can actually, for example, identify inefficiencies and waste that we can quickly find solutions for unexpected events. Like, for example, if we have we have 2 or 3 suppliers who supply us with one product, one material, and we actually have 2 of them that for some reason stopped doing it, something happened. Are we able to then use the other one to supply us with everything that we need? All of these dependencies, if we want to find this information, a graph database can help us get there. The same way, reduce risk of operational disruption. Same situation. Of course, we also want to increase reliability, prevent loss of sales due to failure to meet demand, and in the end, of course, optimize the efficiency between partners and services. Take some water. So, this is exactly the challenge. So, what is the solution? A solution is exactly this graph database that can span the many data sources that we need to get this information, these insights that come from plenty of different tables. So, in this case, for example, in this graph schema here, we have on top locations of factories, and we see already that the colors represent a different data source. Then we have the factory. The factory has, of course, like dependencies with other factories. So, because there are factories that supply other factories. Then we have products, we have shipments, we have companies. And these products have other products. And we see here, like, between all of these relationships, these are all dependencies between the entities. The shipments also have orders, and the orders have sale orders. In all of the entities that we have here, we get exactly to this point when there are so many dependencies that if we want to get any information about, okay, I received the purchase order, am I able to fulfill it? How much, which entities do I have to use? Like, it's being able to create this deep hierarchy and understand much better all of the needs that we have in our business. So this exactly comes to the key supply chain queries that we have, and being able to find the insights to minimize problems that might happen or even anticipate them. And here again, I have like one example that comes up with this solution. For example, in the car industry, typically there are 30,000 parts in a car, since like all the pieces until the engine. And the question is really that we have this compositionality approach where all the pieces are dependent on other parts. And we also have plenty of suppliers. So like, in order to much better have all of these insights about our business and understand if there is any limitation, what can we still do? This is exactly the type of information that we can graph, that we can have real fast with a graph database. In this case here, this is a practical example with real data. That's something that I've worked with. And for example, on top we have two orders, car wheel set and truck wheel set, and in a very simple, not so real, because of course it could be much more complex. We have, for example, all of the materials. So for example, car wheel set use tires use rubber, belts, steel rods, and then the materials. Only in this smart example, we can see like all of the dependencies that we have, and we see how much more intuitive it is also to see the data in this graph that it would be in tables. And this is exactly the power of using graphs, not only for visualization, but also because then, if you want to run our queries, all the data is already interconnected to our needs. And in this case, for example, we see the application of the dependencies, or the order of operation with the chains of dependencies. And also we also can have some queries related with centrality. So for example, imagine if we're having a problem with this site and we want to understand how influent this site is in our network. So for example, if this network goes bankrupt, or if I don't want to do more business with it, can I still manage to do it with all of the alternatives that I have? For example, like changes of price, or I receive a car wheel set order. Do I have enough right now with all of these dependencies to fulfill this order? That's one of the questions that we can come up with. That's the first use case. So the second use case is fraud detection. And again, the situation here, this is the typical money laundering cycle. This is exactly the challenge. And let's start with the collection of dirty money. That is placed into the financial system and then goes into the lowering part. And we see here what happens. What is happening mainly is these transfers and loans and payments to false entities, or sometimes even real entities, but then we start to lose track of them. And we start to lose track of the flow of these transfers because that's exactly the idea, that's exactly what they do, that's exactly what the goal that they want to reach. And of course, after doing all of this money is of course integrated into purchase of luxury assets, commercial, industrial investments, and also financial investments. So this is a challenge. How can a graph help us? So let's start with this graph AML solution, and only this part of the flow of the money, of the transfers, of trying to exactly use distribution problems, of using flow capabilities of graphs to track the money, because that's always the main goal, that we are not able to do it with conventional databases. So for example, here we have these two accounts on top, and through 8 hops we are able to track all the payments and all the accounts that this money has passed by to reach the other 2 accounts with the same money that it was in the beginning. And being able to, for example, if we are able to get this data where we have all of the transfers and we see like it's 10 hops, imagine 8 hops, imagine doing 8 hops in a relational or a dimensional database through like millions of data is super hard, because this data is not interconnected. And in the graph database, because again, from the beginning, because relationships are first-class citizens and we are able to bring all together, we can explore much better and find all of this tracking of the money, of its flow. And that's exactly one of the use cases for graph approach. So another use case still in the same part, comparing a bit with conventional databases. So real-time fraud detection through suspicious activity reports, because that's what most of the entities then start doing. And what is the different thing that a traditional AML solution gives us when compared to a graph-based AML solution? So for example, in this case, we receive a new alert, and from this new alert we have to get other information, so new account. From this new account we get all information, new customer, and you already see 2 hops here. And then we go to a phone number that is part of this account, and also an address and an occupation. And the graph database, because for example, if we receive exactly this new account, we do not have any information about it, because it's a new account. We don't have information about, for example, SARs, about suspicious activity reports that were related with this account. But because once we bring this data into our graph, what happens is this phone number is already an entity. So if this person actually connects to this phone number, and this phone number is already connected to other customers that are connected with some other suspicious activity reports, then this alert will be actually identified as a high risk. Because in a graph database, once you have one data point as a node, as an entity, there is only this one. We don't, everything that is related with this entity will be there, is there in the connector. So if we introduce new data that is related with it, our graph database will be able to instantaneously connect them. So have this information efficiently. And with the situation is exactly like with a traditional AML solution, this would be identified as a low-risk account because he's a new customer. We don't have any history on his financial transactions. But with a graph-based AML solution, this will be identified as a high-risk account because we see exactly that this number is shared with other 4 customers who have alerts turned into SARs. Last use case on the financial fraud. Okay, and here I want to show you a bit. All of this was, of course, like graph exploration, graph algorithms, graph queries. But now, and of course, also a bit joined with graph machine learning. But here is a use case of exactly what these graph features can give us compared to when we are using a table. And the idea, of course, is always to improve accuracy in these anti-money laundering techniques. So, for example, here on the first column, we have alert for counterparty 2. And this machine learning with only account history features defined it as a high risk because this user is part of a high risk geography and it has SARs filed for related accounts. However, when we are checking this information, and of course we are actually able to get more information because in a graph we have exactly all of these relationships and we are able to get more insights from other data sources. What happens is that we see that the percentage of past alerts turned into suspicious activity reports is actually 0%, and this 0% is only able to be reached because of the other use case that I showed you before, because getting this data is much more performative. We actually see, for example, that there are no shared phone numbers, there are no shared address with other flagged accounts. And that's exactly why with machine learning with these deep link graph features would actually be defined with low risk instead of high risk. The middle case is similar, but for example, the last case is the alert for the new customer that I've just also approached before, where we see here, for example, of course, we don't have SARs for a new customer, but we see that when we use the graph, the deep link graph features, we actually can reach that this new user shared phone numbers with flagged accounts. And it's actually because of that identified as a high risk user. And that's a bit of why graphs is relevant and why it's getting more and more important nowadays.
Thank you, Diogo, for your great talk.
Thank you.
So please, the audience, just the quick questions before the conference.
Hi.
Hello.
You have that stuff in production somewhere?
Yeah, there are some. This is being applied, of course, into some of the main banks. They are using these solutions to track this. But of course, I think you're asking this because, of course, this is it's super performative, but at the same time, it's also super demanding because being able to get all of this data. And usually to be able to run these queries, it needs to be in memory, is of course, it requires plenty of hardware and also investment. And, but yeah, like the main banks are using graphs to help them giving these insights and tracking.
I have a question. How do you follow the money if it gets split up and transferred to multiple accounts? Because some of the money, because some of the money could be real.
Yeah, of course. I mean, and for example, that's completely true. And in all the cases, maybe we are with some bad insights. But the idea of this graphs and the idea of solution is to give us better insight of what's happening. Maybe it's not a real problem, but anyways. The idea, I mean, even these suspicious activity reports, they are just reports. They don't really mean that this is fraud. This is really just a tool. I mean, it's used as a tool to give you better insights on all of your data. But of course, then this is used for your analysis for someone who's a specialist. And of course, like then you can go over it and try to really understand with that user, what is really the problem. So sometimes there are false negative, false positive, like with all of the solutions.
Maybe last question? Yeah.
Yeah, I have one question. Thank you very much for the talk. So I was wondering, you have shown very nice examples where, as you said, like interconnected data points can be used for many of the examples, the use case that you gave. I was wondering, can you give us some examples where graphs are a bad representation, where you would say that's not the type of problem that you would try to use graph analysis on it?
Yes, exactly. So that's a good question, because that's usually like the question is more like where graphs start to be a good solution. So like usually, and based on my experience, I say that once we have one problem where we want to do, and we have like a conventional database, and we have to do 1 or 2 joins, it's okay. We know that even if we have huge tables, we know that we are doing 2 joins. There is really not of a big problem. Like we can always find other solutions. The thing is, when we start to do more than 3, 4 joins, and I would say 3, then it starts to get tedious. Tedious?
I don't know. Maybe back.
Yeah, it starts to get tedious, and that's exactly where it starts to make more sense to use a graph data. So I would say it's that part, so it's more like the highly interconnected data, like is it 2 hops, is it 3 hops? So it's exactly in that point.
So, thanks again for the questions.